Hey there, I hope everybody enjoyed your long weekend and able to get out at least early in the weekend. We had some nice weather, a little rainy at the end. So today we're going to do part 2 of topic 3. We did an introduction to spectrum on last day, and today we're going to carry on a little bit further. Tomorrow we'll finish this up with a look at the Doppler effect, finish up topic 3. So spectroscope and studying spectral analysis, we really can study two things. One is the composition of a star, what's it made of, and the other thing is we can tell if it's moving towards us or away from us. Today we're just going to look at the first thing, looking at composition of stars based on spectral analysis. So let's take a look at what we get. So you remember from last time that we can take white light, a combination of all colors, and put it through a prism and get the complete rainbow. We can do that with a prism, or we can do that with a device called diffraction grating. So I did show you some videos on diffraction gratings, and hopefully you have a little bit of information on that. A little bit difference between a diffraction grating. First of all, there is a spectrum on either side of that central equilibrium line. But you'll notice on a diffraction grating, blue doesn't bend very well. The blue end, the violet end, the red end bends a lot. On a prism, the red doesn't bend very well. RRR, red refracts rotten. BBB, blue bends best. And DDD, diffraction, definitely different. Not too important for us in grade 9 science, but just a little mnemonic that you put away for when you get to grade 12. So what exactly was a diffraction grating? Diffraction grating is a device made up of thousands closely placed lines used to produce a spectrum. So that's a diffraction grating. When you look at it, it just looks like a clear plastic. You can't see the little lines that are on it. So, something a little bit new for us. We've got one of the greatest rock stars of all time, Sir Isaac Newton. And he was one of the first people. Other people had looked at it before, but he took a little stronger look at it and held a prism up to the sunlight, to the white light. Isaac Newton passed a beam of sunlight through a prism and produced a continuous, there we go, slight correction there, produced a continuous spectrum. So Newton's experiment showed that sunlight, white light, is made up of the colors Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So if you count those, you'll see that there are 7. These days, quite often, you're going to see Roy G. BV. They're going to take indigo out. A few reasons for that. Indigo is not really a true color. Why did Sir Isaac Newton, one of the smartest men to ever live, include indigo? Well, he was superstitious and believed in the occult and believed in the magic number 7. So when he had just 6 colors, he thought that all science things really should have 7. So he put in indigo, which is just a cross between blue and violet, maybe light purple type of color. So I think in today's bell work, I will refer to the whole Roy G. Biv, the traditional 7 colors. But if ever you just leave out the indigo, for me, that's fine as well. So you have to decide on what your teacher wants from year to year, what you're going to do. So continuous spectrum. So again, looking at the continuous spectrum, how do we produce it? We produce it by taking a solid. Now, if you look at the textbook, they're going to talk about a gas under pressure, which of course works as well. But generally in science, in high school, we make reference just to it being a solid or a liquid that you heat up very, very hot. Pass that through a prism, or it could be a diffraction grating. So the light that's given off by this heated solid or liquid is called white light. White light contains all of the colors, the whole Roy G. Biv range, that continuous spectrum. So continuous spectrum is made by glowing solid or liquid that's just passed through a prism. Second type we're going to talk about is called an emission or a bright line spectrum. And what you do is you take a gas. It's at low pressure, but you heat it up. When that gives off a spectrum, it doesn't contain the whole Roy G. Biv. It has just certain lines of certain colors. So it's just a black background, but then it's got these series of bright lines. That then is called a bright line spectrum. And it's called an emission spectrum as to the nature of the atomic phenomena taking place here with electrons jumping up to higher levels, can't stay at those higher levels, drop down the lower ones and give off light of exact certain color. Each color represents a specific frequency and a specific wavelength. Every element on the periodic table in a gas form will produce a different spectrum of colors. We're going to see how that's going to be used today. So the third is then that dark line spectrum. So you start off with white light produced by a heating solid or liquid, but then before it gets to the prism, there's this intermediate stage. This intermediate stage is the light passing through a cooler gas. So it's going to be through a cool gas. What you then get is from this original, you get the whole continuous spectrum, except there's these dark lines where it's blocked out. Why are those colors blocked out? Because those colors have been absorbed by the cool gas. So the whole spectrum doesn't get through. That light of that particular color is absorbed by this gas. So every different element again will absorb different wavelengths, different colors, different frequencies. So that can be used. Oh, first it's kind of interesting to see the comparison here. So if you take the dark line spectrum for a particular element, and then you took the bright line for it, so again this is the absorption spectrum, this dark line, the bright line or emission spectrum, but if you match them up, the colors would fill in perfectly. So if you just had those colors, you grab this, slide it down, and it'd be a complete continuous spectrum again. So every one of those lines represents a specific color, and that means the color means a specific wavelength, a specific frequency. So identify each of the following. Here would be our bright line spectrum. It's also called an emission spectrum. It's just a black background with a series of colors on it. This is that complete rainbow. We call that the continuous spectrum. So when does red become orange? Where's the intermediate line? It's continuous, so there's not exactly a particular line. And this color of red has a different wavelength than this red and this red, just like we see that in real life. And then we have the dark line spectrum. The dark line spectrum appears to be a continuous spectrum, except there's dark lines blocking out certain colors. It's also called an absorption spectrum. So what exactly is spectral analysis? By comparing the known dark lines, spectra of various elements, with the spectral lines of those given off by a particular star, we can determine the composition of that star. So we're going to do an example of that. But here you've got, for hydrogen will always have those three dark lines. By taking a specific star like the sun, we can then determine which elements are there. Let's take a closer look at how we do that. So here we have, let me just move that down out of the way. Here we have for hydrogen. If hydrogen gas is present in a star in the outer atmosphere, then these three lines will be darked out. So what happens is the continuous spectrum that was going through it has these three wavelengths, three colors absorbed by the cool gas on the outside. Helium always has these four lines. Sodium, just two lines. Those two right there. Calcium, 1, 2, 3, 4, 5 lines. Mercury, 1, 2, 3, 4 lines. So if mercury gas is present in a particular star, and you'll get an episode like that today in the bell work, all four of these lines must be present. So let's take a look at our sun. So here is the dark line spectrum that is produced by our sun. So let's take this first line right here and see where it matches up to. Nothing from mercury, nothing from calcium, nothing from sodium, nothing from the element helium. Oh, look here for hydrogen. So for hydrogen, that's what that line would possibly be there for. But if hydrogen is present, these other two lines, all three, these other two lines must also be present. So let's check to see if this one is there. Oh, carry on down. Sure enough, that line represented right there as well. But is the third one present? Here's the third one. Take it down. It's present as well. So therefore, we can say, yeah, hydrogen is present in our sun. let's check in the outer atmosphere of our sun. Let's take a look at helium. For the second line, sorry. Kind of gave you the answer away. Second line, shoot it up, and here it is. You can find it on helium, but these other 3 lines, all 4 lines must be present if helium's there. So let's check the next line, see if it's found there. It is indeed. The third line, also there. Fourth line is pretty good guess. Yep, so all 4 lines of helium are present. 1, 2, 3, and 4. So helium is also present in this gas. Sodium only has those 2 lines, and you can see them standing right there. So that means sodium is also present. Take a look. That's all of the lines accounted for. So calcium, take it down, not present, not present, not present. Clearly calcium's not there. And mercury, there's no line outside there, none there. Those 2 aren't there. Clearly calcium's not there. So our sun made of 3 principal gases: hydrogen, helium, and sodium. So that's all we're going to do today, folks. About 11-minute video. We'll do some bell work on that, and tomorrow we'll come back and see how we can also do spectral analysis using the phenomenon known as the Doppler effect. And the Doppler effect is going to tell us whether a star is moving towards us or if it's moving away from us. So take care and stay well.